Here's integrated 3 lecture for 10.2.2. It says, what if n is very large? So we're going to learn about infinite geometric series today. And it starts out with this first problem. It says, what is the vertical distance a ball will travel if you toss it up and let it bounce? What if a bouncing ball continues to bounce forever? How far will it travel? Today you will discover ways to represent this situation and answer these questions. So we're just going to do this first problem, and then I'm going to do a little mini proof for you to give you a formula. I think that'll be it for today. So imagine you're lying on the ground and tossing a ball straight up 10 meters. When the ball gets back to you, how far has it traveled? Well, it had to go up. It had to go up by 10, but it had to come down by 10, so 20. And then it says, instead of catching it, imagine that you let it bounce. The ball has a bounce ratio of 60%, meaning that each time it bounces, the ball will bounce to 60% of its previous height. When the ball comes back down to you the second time, how far has it vertically traveled in total? So I know you can see the answer right there. I'll explain how they got that answer. So the first time it bounced, or the first time you threw it up and it came back. You threw it up by 10 and it came back, but then instead of catching it, you let it bounce back up, but it only bounces 60% of the height that it, started with. So 60% of 10 is 6. So it went up 6. And then it has to come down the same amount. So this is really, so this first, term is 1. This is the first term, it's 20. Second term is 12. If I did let it bounce again, it would bounce, 60% of 6 is 3.6. It'd go up and down by 3.6. So it would really be 7.2. So we have 20 plus 12. They're only asking about the first two. They're just asking if you threw it up, let it bounce, and then let it come back to you. Then you would have 32 on letter B. And then letter C says, imagine you let the ball bounce 15 times. Write a geometric series to represent the vertical distance the ball travels until it comes back to you the 15th time. So we already kind of learned this in the last video, in the last lesson. There's a math notes box on page 538, but if it's a geometric series, if it's got like a, y equals a times b to the x, if it's kind of an exponential, this is like exponential decay, by the way, then here is your formula for that. So a is the first term, r is the multiplier, and then you have to put n minus 1 because that's the first term. If you let that be the 0th term, then that could just be n. But if you get in the habit of making a the 0th term, then you're going to get into trouble with the formulas that you have, because the math notes box likes to show it this way. So just to always think of a as the first term, and then you have to put an n minus 1 on your r. So if I want to make this ball bouncing situation into a geometric, if I want to get a little formula for it, I would say, I didn't even write it anywhere. What would it be? It would be 20, because that's the first term, and r is 0.6. This is how I get any term that I want. Like if I wanted to find what's the 5th term, I just plug a 5 in. Or if I wanted to find out the 10th term, I could plug a 10 in. But they actually, if they can, the way they asked the question, they said, write a geometric series they want me to actually write the whole series to represent the ball as it travels 15 times. So they actually want you to write, 20 plus 20 times 0.06 plus, I wrote it like this, 20 times 0.6 squared, and the next one would be 20 times 0.6 cubed, and you would just keep going all the way. I ran out of room, by the way. There's 20 times 0.6 cubed, 20 times 0.6 to the fourth, blah, 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 keep going, dot, 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 until you get to the n minus 1. Well, remember, we're trying to do 15 terms, so 15 minus 1 is 14. So 20 times 0.6 to the, that's a little 14, it's hard to tell. Okay, so that right there is what you would write if they told you to write the whole series. You just have to write a dot, dot, dot. And then letter D says, what is the total distance the ball will travel up and down? Well, we have a formula for that, and it's in the math notes box, and we talked about it in the last video. The formula to sum up all the terms of a series, and a finite series, I would just plug in 15 here, because I'm looking for the sum of 15 terms, and I plug in a 15 here. R would be 0.6, and A would be the first term, which was 20. Okay, so that's what I did here. I just plugged them into that formula right there. And I showed all my math. Like, I hope that you guys know that you have to use the order of operations. So this would be 0.6 to the 15th, which is this crazy number right here. And then you have to go 1 minus that number, and then you times it by 20, and then you divide by, that's 0.4. Okay, or you can type it all carefully into your calculator, and you don't have to show all your intermediate steps. But notice that we get, if you let the ball bounce 15 times, it'll travel about almost 50 meters, 49.98 meters. So keep that in mind, and we'll go back and look at that again. Now I'm going to just give you kind of a, I guess I'll start out with what I'm trying to give you, and then I'll go back and explain where I got it. I'm trying to give you, oh, that looks horrible. That's an infinity symbol. This is the sum of an infinite number of terms, would be A over 1 minus R. So if I don't stop the ball, and if it just doesn't stop bouncing, it would bounce a shorter and shorter distance each time. I think I'm going to have you actually read a little bit of this so you'll understand what I'm talking about. It says, of course you know that a ball cannot bounce forever, but imagine the ball in the previous problem can. Thinking about this possibility has led to some interesting discoveries. Will the total vertical distance the ball travels up and down continue to grow larger and larger? Now imagine moving according to the following sequence. Move 20 units to the right, and then continue moving right, each time moving 60% less, or 0.6 times the distance you moved previously. You'll notice that I've probably done this in class before. If I don't know if I've shown you this in class before, where I try to get out the door, but I can never get out the door because I keep cutting my distance in half, and in half, and in half, and in half. And it's a paradox, but that's kind of the situation that we're talking about here. So they're saying, would I be able to sum up an infinite number of terms of a ball bouncing, if it just kept bouncing a little bit, like 60% of, it would just keep bouncing a smaller and smaller amount each time. So I'm going to show you, I think, this. So here's like a little proof that I can actually find out exactly how far that ball would bounce if it could just keep going infinitely. And you're going to be, well, I don't know if you'll be surprised or not, but it's very, very close to this amount. And so if I show the proof of that, this is our series. Remember, we started with 20, and then we went 20 times r, which was 0.6, then we went 20 times, well, really, it's whatever this was is that, but then it's times 0.6 again, so you can show it like this, like 0.6 squared, 0.6 cubed, or whatever. So I just wrote down the series, but I wrote it to the infinite. Like I'm saying that it keeps, I shouldn't even write infinity minus 1. I should just keep it, show that it's going on forever and ever. And then I'm going to add to it, or, well, I guess you could say I'm going to subtract from it r times the series. So instead of subtracting, I'm going to add the opposite. So if I times r by this top series, actually times it by negative r, then this one times negative r makes that. This times negative r makes that. This, there's going to be all these cancellations, right? But if this goes on forever and ever, and these go on forever and ever, won't they just keep canceling forever and ever, and there'll never be a last term? So you'll end up with all this stuff canceling out, and you'll just have a right here on the right side. And then here you'll have s sub infinity minus r times s sub infinity. So if you factor out the s sub infinity, you'll have s sub infinity times 1 minus r is equal to a, and then you divide both sides by 1 minus r. So if you didn't really understand the derivation, well, I think you're still going to be able to do the math. Just basically, this is going to be in one of your math notes boxes. This is how you can sum up an infinite series. So if that ball keeps bouncing forever and ever, but it keeps only bouncing 60% of the previous bounce, I can find out exactly how far it went. This was how far it bounced if I just let it bounce 15 times. But I'm going to let it bounce, what was A? I'm going to let it bounce infinite times. That's infinity. So A was 20 in this problem, remember? 20 was A. And then R was 0.6. So that is 20 divided by 0.4. And that ends up just being 50. 50. Now, isn't that so close to 49.98? Because the longer you let it bounce, it's just adding this tiny, tiny, tiny minute amount. So this is another formula that we're going to be using, and I'll probably talk a little bit more about that next time. And if you wanted to mess around with that to just prove that it works, I went ahead and plugged in like what would happen for the 100th bounce. So I just went and did all the math for the 100th bounce, and it came right out to 50, just like this formula did. So basically right here, this is the sum of an infinite geometric series. Okay.